Yo, here we go. I'm sitting in the dark because we're doing the scary problem. Probability. Scary. Just a little math. We got this. Nothing to be worried about. Anyways, let's do it. So, we got 2018, number 3. Good one. Pause it up. Check that out. Then, do it. Pause the video and do that whole problem yourself before we go over it. All right, so we got a situation here where 3.5% of people in some region are from multiple births, twins, triplets, whatever. Then we've got some information about the people. 22% of those from multiple births are left-handed, and 11% of the single births are left-handed. So A is asking us what's the probability a randomly selected child born in the region is left-handed. B, what's the probability a child in the region is a child from a multiple birth given the child is left-handed. And C, we're given 20 children. What's the probability the sample will have at least 3 children who are left-handed? So before we even jump into any of these individually, few things. So first off, a lot of students I've seen get confused by this in the region, but all this information is just about some certain region. So when we read this question, right, we don't really care about the in the region part, right? So I've seen students get thrown off by that. So that's the first thing, right? Whatever. Everyone we're talking about is in this region. So the next thing is when we read A here, what's probability someone's left-handed, right? So we have to consider the fact that there's left-handed people who are from multiple births and left-handed people who are from single births, right? So hopefully we got some ideas about this. For B, what's probability a randomly selected child born in the region is a child from a multiple birth given the child is left-handed. So hopefully this word given is jumping out at us. That's a clear indication we're going to have some conditional probability, right? So here we're going to have some kind of conditional. And then in C, notice we're given a sample size. We want the probability that the sample will have at least 3 children who are left-handed, right? So we're given an N. We're given a number of successes here. We've got an at least or at most question. So hopefully we're recognizing that this is some type of binomial probability. So those are some of the things that maybe are floating around in our heads. Now, B and C both require the probability that a kid is left-handed. So let's pretend you're taking the exam. If you're like, I know how to do C, but I can't get the probability someone's left-handed in A. Make up an answer to A, right? It's going to be incorrect. It's going to be wrong. And it's got to be reasonable. It's got to be between 0 and 1, but whatever, 0.25. Say that's your answer to A, and then use that answer, that made-up answer in part C, and you can still get essentially correct for part C. So that's a little test tip you might need, because one thing that stands out to me about C is that you can, right, you need the answer from A to do C, but you might understand binomial probability without necessarily being able to do A or B. You know how to do some calculator stuff. But anyways, moving on, let's jump into the details here. So there are a couple ways we could go about this. What's the probability a randomly selected child born in the region is left-handed? So we got a couple things going on. So I'm going to jump over to my whiteboard here. You can see my sloppy handwriting. Getting ready. So before we could, right, there's are they left-handed or not? But before we know if they're left-handed or not, we have to know, were they from a single or multiple birth? I don't know why it was so hard to speak English right there. Or another thing we might think about is that these are conditional probabilities. This is the probability someone is left-handed given they're from a multiple birth. And this is the probability that someone's left-handed given they're from a single birth. So the fact that I'm given conditional probabilities tells me I can create a tree diagram. Or if that doesn't work for you, the fact that we have 2 events going on, one after the other. First, we got to know what kind of birth you're from. Then we got to know about your handedness. That idea that we have the sequence of events, right? Type of birth, handedness, that also suggests to me I could use a tree diagram. You don't have to, and in a minute we'll look at how you can do it without the tree. But, right, a lot of us, I'm a visual person, I like the tree. So the first thing we have to know about a person, right, is are they from a single or a multiple birth? And I strongly recommend using words on your tree diagram. Oftentimes I see students who have a good tree drawn, but it's all numbers, and then when they start to do problems, they use some of the wrong ones. We know that from this, right, from the given context, 3.5% are from multiple births. So the probability from a multiple birth is 0.035. If 3.5% of births are multiple, that means the rest of them, 1 minus 0.035 or the other 96.5%, whatever, the rest have to be from single births. All right, so whenever we split off into two branches in our tree, these two probabilities have to add up to 1. So that's the first thing we have to do. The next thing we have to think about is handedness, lefty or righty. So it tells us that if you're from a multiple birth, 22% are left-handed, which means if you're from a multiple birth, the other 78% are right-handed, right? All these two numbers, right, when your branches split into 2 or 3, however many branches, right, when they split like that, probabilities on those splitting branches have to sum to 1. And if you're from a single birth, 11% are left-handed, so that means the other 89% are right-handed. So these probabilities in green, these are all conditional probabilities, right? That's what a tree diagram shows us. This is the probability you're a lefty given you're from a multiple birth. Probability you're a righty given you're from a multiple birth. Probability you're a lefty given from your single birth, and so on. When I use a tree diagram, I like to calculate these and these red numbers. So to work with the tree diagram, we're going to multiply across branches. So to get this top spot, I'm going to do 0.965 times 0.11. When we use a tree diagram, multiplication is implied, and I definitely should have figured all these out before I started this video. So this is 0.10615. 0.965 times 0.89 is 0.85885. 0.035 times 0.22. 0.0077, and 0.035 times 0.78 is 0.0273. These red numbers should all sum to 1, so I'm just going to double check that and make sure that I didn't make a mistake anywhere, because that would probably make this a terrible video. Good. They sum to 1. There it is. It's dark. I'm good. So these red numbers, these are all and probabilities. Like this top number, this is the probability someone's from a single birth and they're left-handed. This bottom number, this is the probability they're from a multiple birth and they're right-handed. So the red numbers are all and probabilities. Our question was, what's the probability someone's left-handed, regardless of type of birth? So we want to now figure out what's the probability someone's a lefty. And if we look at our tree diagram, there's 2 spots that represent lefties. This top number and this number right here. If you're going to create a tree diagram, you can do every single problem just pulling out these red, like far right and probabilities here. All right, so sometimes a common mistake I see is students start pulling numbers out of like the blue and green out of the inside of the tree. All right, it's possible to do things that way, right, if you really understand what's going on. But you know, if you're struggling in the beginning, right, as you're figuring everything out, you can do every problem just using now these red numbers. And that's what I'm doing here. So we've got this number for lefties, 0.10615, or these people were also lefties, 0.0077, and that's how we get our final answer of whatever it is. And that's it. That's part A. These probability questions are easy to score. To get essentially correct, get the right answer. Couple things, make sure you show the addition. With the tree diagram, the multiplication cross branches is implied to get these red numbers here, but that addition is not. So don't be the person who gets like partially correct because you have the perfect tree and everything and then you just write the final answer. Don't be that guy or girl. That's like the most devastating thing to your teachers. You know how to do everything, but you're lazy and didn't show all the work. All right, so that's A. Now we know 0.11385 is the probability someone's left-handed. Let's jump over to our scoring and just kind of peek at the details and find out if I should stop this video and start it over because I got the wrong answer. Let's see. Boom. Probability is correct and work is shown with values using a formula, a tree diagram, or some other strategy, right? Boom, we got the tree and that's it. And I didn't put the actual number in here, but don't worry, that's the right answer. I was just like, you know, making it seem like maybe it wasn't. All right, boom. Notice down here it said you have to include the summing of two multiplications. What am I doing? What am I doing? That's not what I meant to do. So next up, we want to go to part B. Sorry, I paused for a second. I'm wondering, like, did I share the right screen? So now we want the probability of a randomly selected child born in the region is from a multiple birth given the child is left-handed. Oh, no, we don't want to do that. No, we don't. I'm sorry. Let's go back to A. You didn't need to use a tree diagram for this. Here's another way you could have done part A. Sorry about that. Got really excited. You could be from a single birth and left-handed, or you could be from a multiple birth and left-handed. Now, this is the same exact thing that we did without the tree, right? But like mathematically, it's the same stuff. We're not doing anything different here. So from here, there's just a lot to think about. So I like the tree because we can visually see everything, right? But you could do it this way. So overall, if 3.5% are from multiple births, so that's what number is going to be over here, 0.035. Then the other 96.5% would be from single births. So this is 1 minus 0.035. And then we're always going to is going to imply multiplication. And then we know that if you're from multiple births, 22% are left-handed. So over here we would multiply by 0.22. And if you are from single births, 11% are left-handed. So over here we'd multiply by 0.11. And when we multiply these, that was that 0.10615 that we pulled out of the tree diagram, right? Or means add. And this was that 0.0077 that we pulled out of the tree. So you could do this without a tree diagram, right? That's the same work that we did, and just kind of translate everything into words. Right? You do what works for you. I like the tree and visual. It does add a little extra. Like we did calculate some numbers we didn't end up using. So do what you're comfortable with. All right, now for part B for real. So part B was that conditional. And I know part B is conditional because I see the word given. So for part B, we now want the probability that a randomly selected child born in the region is from a multiple birth given they are left-handed. All right. So if we want to translate that into some conditional notation, now I'm leaving my tree there because I'm going to use that. We want the probability, let me just double check, probability that the person is from multiple births given, remember that means given, they're left-handed. So for any conditional probability, I don't know why I made that a T. I don't know what left-handed means. For any conditional probability, it just becomes applying a formula. So for any conditional, we want to do the overlap or both, or the probability of A and B divided by the given thing. So if I wrote this as the probability of A given B in red, the formula would be the probability of A and B over the probability of B. Or in our context, that means we want the probability someone's from a multiple birth and they're left-handed divided by B, the given thing, the probability they're left-handed. Right? And that's how every conditional works. I tell my students, if you can write this conditional notation, from there, the math is just a formula. The top number, right, the numerator is always both or the overlap, right, however you want to think about it, or the and probability. And then the denominator is always the total for the given thing. So to get these blue numbers, we're now going to come back to our tree diagram. So the probability that someone was from multiple births and left-handed, that's this right here, right? So when we use our tree diagram to do this Bayesian probability, this conditional stuff, we're going to only use these red numbers, as I mentioned. I'm doing that like a lot, huh? Only use these red numbers, these and probabilities. So the numerator, probability of multiple births and left-handed, that's the 0.0077. And our denominator, which I will do in green, probability of left-handed, that was our answer to part A, right? That was from 0.0077 plus 0.01, what that says. what that says. Right, so this is that 0.0077 plus 0.10615, and I now realize you can't see anything that I'm writing. All right. Now I know we had this answer, right? We have that 0.11385 or whatever it was, but I wanted to show the addition because with any conditional with a tree diagram, right? If you show the addition in the denominator, you're always going to see this number repeat. So if that number doesn't repeat in both the numerator and denominator, like there's a mistake, right? Because this is total left-handed, the denominator, and the numerator is multiple births and left-handed, right? So these, right? This is part of this, and that's what we're seeing here. This numerator is part of this total in the denominator. So that gives us 0.0077 over 0.11385. That answered A. It's okay if you just wrote 0.11385 down here, right, from A. Obviously, we already did that work. I just, went overkill and shown that to see that repetition. And so we get this 0.0676. Cool song I played. All right, let's finish this thing up. So going back to PowerPoint here, smart notebook. All right, I get it. I can't use the real one. It's limited. Get on my face. Essentially correct if probability is computed correctly. Boom. With work shown. Boom. With correct numerator and denominator. I mean, I guess that's going to happen if we get the right final answer probably. So we're good. And notice it says appropriate values include incorrect values from part A. So that idea I mentioned earlier of if you use a wrong answer from A in subsequent parts, right, like that's okay. You're still going to get, right, that's still appropriate for now for parts B and C. So last up, part C. Got a sample of 20 children with probability at least 3 are left-handed. Keeping in mind, that was ridiculous and also kind of hurt. Keeping in mind that the probability a child is left-handed in this region is 0.11385. All right. So here, we want the probability at least 3 of these children are lefties. So the first thing we have to think about, right, like, what's at least 3 mean? At least 3, we've got 20 people. At least 3 means 3 or what? Or more, right? So 3, 4, 5, 6, 7, 8, all the way up to all 20 are lefties, right? This is what we want the probability of. 3, 4, 5, 6, 7, 8, 9, 10, all of them are lefties. Now, hopefully you realize I could do like a bunch of binomial PDFs, but that would take forever. Or I could calculate all these binomial probabilities individually. I could find the probability exactly 3 are lefties out of 20, exactly 4 out of 20, exactly 5 out of 20, right? That would be ridiculous. So instead, the only things that aren't included here, the only possible numbers of lefties that don't satisfy at least 3 would be 0, 1, or 2 lefties. So what we want to do is we want to find the probability that there's 0, 1, or 2 lefties, but at least 3 is not 0, 1, or 2, right? At least 3 is everything else. So at least 3 is the same thing as not 0, 1, or 2, right? That's what we're seeing in this list. At least 3 is literally everything except 0, 1, and 2. So not 0, 1, or 2, which means we're going to subtract. Now, to get the probability that there's exactly 0 lefties or 1 lefty or 2 lefties, right, that's doable. If I could, right, if there's no lefties, I got 20 people, righty and righty and righty and righty and righty, right? All 20 are righties, so this is going to be probability of a righty is 0.88615 to the 20th, right? Righty to the 20th power. To get the probability exactly 1 lefty, I'm going to 0.11385. That's my lefty. Well, I want 1 of them. That means the other 19 people have to be righties, but I then have to consider the fact, right, this only accounts for that one arrangement, right? This only accounts for one possible way that there could be exactly 1 lefty. Well, if we have 20 spots, how many different arrangements could we have? How many spots could this one lefty be in? 20. And that's what 20 choose 1 would give us. And then I could get the probability that there are 2 lefties. Now I have 0.11385 to the second power, 0.88615 to the 18th, right? So there's 2 lefties, the other 18 are righties. But then I got to do 20 choose 2 to get the number of arrangements, the number of different ways I could get exactly 2 lefties amongst 20 people. I would then add these 3 answers. I have run out of colors. Do I have a purple? No. And subtract from 1. Literally no other colors in there. So I could add these 3. I get that sum and subtract from 1. Now, the reason I did that kind of quick and didn't go too deep into it is because that's not what I would do. That's probably the most time consuming, and it probably also makes sense, right? 2 lefties means 18 righties times the number of arrangements, right? So that's why I wanted to start there. We've got another option. To get 0, 1, or 2 lefties, I could use my calculator. So if you remember, this is binomial probability because we're given a sample size, we're given a number of successes. So I could do 3 separate binomial PDFs. I could do 3, if I do that, I have to label this as my sample size or my number of trials, which is 20, comma, the probability of a lefty, which is 0.11385. And then the third thing is my number of lefties. So I could do this 3 separate times with 0 at the end, then for exactly 1 lefty, then exactly 2 lefties, right? And this would all be the same. This is probably how I would show my work on the exam, right? Hopefully that's okay. And I would add these 3 probabilities. So this conceptually, right, if we are going to use binomial PDF, CDF in the exam, we have to label these things. So this is super important, these labels. And then I subtract that from 1. Conceptually, this is the same thing as the work that I just showed. We're just using a calculator function to do the arithmetic for us. So this is the probability we get exactly 0 lefties out of 20. This is the probability we get exactly 1 lefty out of 20 and exactly 2 lefties out of 20. By adding those, we're getting 0, 1, or 2 lefties, all this green stuff. But then we want to subtract from 1 because we don't want 0, 1, or 2 lefties. We want, right, at least 3. So theoretically, I could do this binomial PDF thing for 3, 4, 5, 6, 7, 8, 9, 10, all the way up to 20 and add all those. That just takes too long. And then comes my third option, the one that I personally would do on the exam. If we recall, binomial PDF was to get an exact individual number of successes that we just used. But binomial CDF, right, that CDF stands for a cumulative probability, or a probability like to the left. So binomial CDF cannot give us our answer because we want a probability like to the right, right? Like we literally want from 3 and above. So we're going to use binomial CDF to find from 2 below a probability to the left and then subtract from 1. So what I'm actually going to do on the exam, binomial CDF, my number of children, my number of people is 20. Did I write number of lefties before? I hope not. If I did, go back in the video and that was wrong. It should be number of people, number of trials, number of children. My probability of a lefty is 0.11385. And then my upper bound, it's called, would be 2. And so that's going to give me 2 as my upper, or 1 or 0. I'm going to get that answer and subtract from 1. That's the most efficient way we could calculate this probability. On your calculator screen, it doesn't say these, right? I tried to put these labels in context. This is our N, our number of trials. This is our P, our probability, and this is just going to say X. But that's right, our upper bound, like our maximum number of lefties. So I think here, if we wrote like max lefties, I would assume that would be okay because that's just what that number means in context. All right, that's how we answer that. We should probably actually do it, right? So let's see, 1 minus second bars, binomial CDF's down here, and is 20.11385. There's that X I mentioned. So 1 minus all that gives us 0.402. Done. Marker drop. Yeah, so hopefully we got the right answer. I mean, again, the probability ones are easy to score. Use calculation of the binomial. Yep, we did that. It's important we label as binom PDF or CDF, or we showed those arrangements in the original, the first way I showed. Right numbers for N and P, correct endpoint value. That was the 2 we used. Correct direction. I mean, we did that with CDF was kind of to the left, and then correct work. I mean, I know we got essentially correct because we did all, like we did it all right. And that's it. Come back some other time and we'll do number 4. So that's the end of your scary story in the dark for today.